In the last video we looked at the binomial distribution, and in this video we're going to use that binomial distribution to do a hypothesis test for a population proportion. So the example is on mouse genes, and we can take a look at the data that we're working with. And the variable that we're interested in is this one, and that tells us in our sample of genes whether the gene is not on the X chromosome, which is a no, or if it is on the X chromosome, which is a yes. And so if we tabulate those values, we end up with 15 no's and 10 yeses. So we've got 10 out of 25 genes that are on the X chromosome. And so if the genes were randomly occurring throughout the genome, then we would actually only expect 6.1% of the genes to be on the X chromosome. So we're getting a result here that doesn't appear to support the notion that the genes are occurring randomly throughout the genome. And so to test this, we're going to do a formal hypothesis test. And first step is to state the hypotheses. So the null hypothesis is that the population proportion P is equal to 0.061. The alternative hypothesis is that P is not equal to 0.061. Our test statistic is the number of genes in our sample that are on the X chromosome, which is 10. And then our p-value, we're going to use the binomial distribution to figure out the probability under the null hypothesis of getting something as extreme or more extreme than 10. So we're going to mimic some calculations that we did in the last video when we looked at calculating binomial probabilities. So n is our sample size, p is our population proportion, 0.061. X successes is a vector going from 0 up to the sample size. So I'll just show you what that looks like. And then we're going to use the dbinom function to calculate our probabilities. And then I'm just going to round the results so that we can see things a little more easily without getting encumbered by scientific notation. Okay, so there's our probability table. So if the population proportion really was 0.061, the probability of getting 0 genes on the X chromosome would be 0.2073. Probability of getting 1 gene on the X chromosome is 0.3367, and so on, and all the way up to probability of getting all 25 genes out of the sample be on the X chromosome. It's a very small number, 0.0000 to 4 decimal places. Okay, so that's a table of probabilities that we can use to calculate our p-value. And our p-value is the probability under the null hypothesis of getting something as extreme as our test statistic, or even more extreme. And so remember, our test statistic is that x equals to 10. And so if we add up the probabilities of 10 or more, and then multiply that by 2, because we're doing a two-tailed test, that will give us our p-value. And just from looking at this table, we know we're going to get a small number because all these probabilities are 0 to 4 decimal places. So we're adding them up, we're going to get a pretty small number, and sure enough, we get 1.99 times 10 to the minus 6, a very small probability indeed. So that's our p-value, and then our fourth step is to make a decision and draw a conclusion. So our decision rule is reject the null hypothesis in favor of the alternative hypothesis if the p-value is smaller than our significance level, which we'll set at 0.05 as usual. And otherwise, if the p-value was larger than our significance level, we would fail to reject the null hypothesis. So in this case, we're getting a p-value smaller than our significance level, so we reject the null in favor of the alternative. So there's sufficient evidence at a significance level 0.05 that the population proportion p is not equal to 0.061 for these mouse genes. Another way of doing this without having to calculate all these probabilities by hand is to use this function here, binom.test, and we can take a look at what that function does here. So it performs an exact binomial test, and here's all the details. Here's the arguments that you need to use. This is what the test returns, and then there's some examples down here. So in this case, we kind of have to fudge it a little bit to get our p-value, because we're going to use this argument here to actually calculate the upper tail probability, the upper tail p-value, and then we'll multiply that by 2 to get our two-tail p-value. So if we do that, we get exactly the same number that we got when we calculated it, kind of longhand. So that's how to perform a binomial test for a population proportion in R.